All right, what we're going to look at here is what's called the normal probability distribution. And the normal probability distribution is a otherwise known as the bell curve, or the mathematical function that drives it is the Gaussian. And so what we're going to do is define this and have it work out for us. Let me get this on the screen a little bit better here. There we go. And I'll adjust this downwards so it all fits on the screen there. That's better. And so come back here. There we go. So, and what we're going to do is we're going to invent a way of dealing with this distribution. And so in chapter 4, we dealt with discrete probability distributions. We're going to deal with continuous random variables. So if we looked at the example where we had how many calls were given in a day, and that was discrete, and there were gaps in between each possible number, we're going to look at a continuous probability distribution. So that the thing that we're measuring can continue in between numbers, and so it's measurable. There are no gaps. And so probability becomes a little bit different here. We have to start thinking about area and not just the number of things that we use. And so the first distribution that we really look at is going to be called a normal distribution. Again, this curve is called also called a Gaussian or a bell curve. And this is the most important curve that we'll use in statistics. We'll come back to it over and over again. And it has this shape here. And there are some points of interest on this shape. It has a center, and it's symmetric on either side of the center. And that center is usually where we'll put the mean. And so some properties of how things are spaced out in this distribution: the mean, the median, and the mode are equal. The curve is bell-shaped and symmetric about the mean, and the total area under the curve is 1. So if we think of coloring in the blue area, it's going to be 1. And that relates back to probabilities. Probabilities of 1 are 100% guaranteed. So under this curve, what's underneath this curve will cover every possible value that we can have. And where it's wider or thicker, if it's taller, there's more area or more probability of being in that area. The normal curve approaches the x-axis, but it never touches it. Even though in this graph it stops here, this line keeps going on. So this thing goes off to negative infinity and positive infinity. Now, what we can look at is we can think of the mean and talk about standard deviations. And between the one standard deviation, there's inflection points. So above this inflection point, it's concave down. It's a bowl shaping down. But when it turns at these inflection points, it turns to being concave up. It's a bowl shaped upwards. And these inflection points, or where it turns its curvature, happens at one standard deviation away from the mean on either side. So sometimes when I draw these by hand, I think of drawing little Pac-Man ghosts, and I have to curve downwards, and as soon as I hit that inflection point, I switch my hand to curving upwards. Now, what we will talk about is a probability density function. And so a discrete probability can be graphed with a histogram. But for continuous probability distribution, we use a probability density function. The function can never be negative because it gives out a probability, and the total area of a probability density function has to be 1. Just like probability distributions in chapter 4 had to add up to 1. And so what happens is the standard deviation describes the width. And so here we have some different normal distributions, and they can have any mean that we want. And so here we have a mean of 3.5 and a standard deviation of 1.5. Here we have the same mean, but a smaller standard deviation. So this curve narrows. It's not as wide. We can think of the standard deviation as describing the width. We talked about some of this in Chapter 2 when we did descriptive statistics. Here we have the same standard deviation as this normal distribution, but the mean is shifted over to 1.5. So if we look at these two curves, which one has the greater mean? Well, A has the greater mean because the center of this curve is at 15, while B, the center of this curve, is at 12. So the greater mean is the curve where the center is further along the x-axis. If we look at the greater standard deviation, A is narrow, so it has a smaller standard deviation, and B is wide, so it has a larger standard deviation. So if we look at the test scores on a mathematical test for New York for grade 6, if we want to know what the mean is, we look here, and the mean is at 600. And if we want to find the standard deviation, we have to look for the inflection point. And so we have to kind of estimate where the inflection point is. And we can do this. It's about, it seems to turn about here. So what is that? 560, 570, 580, 590, 600. So my inflection point's about here. So that's 1, 2. That's about, it looks like we have a standard deviation of about 20. And if we draw here these inflection points, we have a standard deviation of about 20. If we go back to our empirical rule, the percent of stuff in between one standard deviation is 68.13%. And we can start thinking of that as a probability of falling within these areas. And so using that empirical rule, we think there's about 68% of the stuff in between here. If we go out to 2 standard deviations, there's about 95% of the stuff. And if we go out to 3 standard deviations, 540 and 660, there's 99.7% of the stuff. And so that's the probability of lying between those two values. Now, all of these normal curves have different heights, and but their areas end up being the same. And so what we can do is we can standardize this. We can do some things where we're always going to guarantee that the area is 1, and we're going to give it a mean of 0 and a standard deviation of 1. And so we call this the standard normal distribution. We create a curve where the mean will always be at 0, and the standard deviation will be 1. That means we can take any measured value and we can transfer it to the standard normal. So we can say that any x value can be turned into a z-score, just like we did with descriptive statistics. We take the value minus the mean and divide it by the standard deviation. So if we look back into our notes in Chapter 2, we had a way of calculating a z-score for anything that we knew the standard deviation on. And so the standard normal distribution is kind of a translation object. We can get the actual mean we have and our actual data value, and we can transfer them to z values using this z, and we can talk about our distribution as it relates to the normal distribution. And so the standard normal distribution has a mean of 0, standard deviation of 1, and the total area over the curve is 1. This will give us some things that if we get down to a z-score of about negative 3.49, we're very close to 0 for most of the things we're doing with. And if we get to a positive score of 3.49, we're also close to 0. And so we can say that anything from z equals 0, the middle point, if we color in z equals 0, all of the stuff coming before it is 50%, or the area of everything up until 0 is 0.5. And if I get really, really close to z equals 3.49, the area under the curve is really close to 1. And so what happens is all the standard normal tables will always be the same. If I know a z-score, I can talk about the area of the curve up until that z-score. And the back of your book has some tables to work with this. So if I have a z-score for 1.15, I come down to 1.1, and I add the 0.5 to it, and that tells me that the area under the curve from negative infinity to 1.15 is approximately 0.8749. And that's for positive z-scores. If I have a negative z-score, so negative 0.24, I come down to negative 0.2, and I go over to the 0.4, and the area under the curve from negative infinity to about negative 0.24 is 0.4052. And these scores can become a probability. A really important thing when trying to find the areas under a normal curve is to always draw the region you're looking for. And so if we want to find the area contained within a z-score, and the area is going to be a probability when we're done with it, we're going to be getting everything to the left. So you sketch the normal curve, and you approximate where your z value is, and everything to the left is what's going to be shaded in. And then you look up the value in the table, and you turn that into a probability. So we're going to look at, let me get onto my normal curve here. We're going to look at finding areas under the curve if it's to the right of a distribution. And in all of these, we'll use a table. So let's take, let's go to Excel for this, since Excel is our best calculating tool. So let's start with this idea that we have a z-score. Z equals 1.23, and we want to find the probability to the left. So what we normally do, and let me make sure my pen is working here, is we start by drawing our normal distribution. My little Pac-Man ghost, where here is the mean, which is going to equal 0. So positive z-scores lie to the right of that. It's not showing up here. Let me see if I can get my, there we go. Get that to show up for you here. So a positive z-score of 1.23 is going to be past the inflection point and about here. Z equals 1.23. And so I'm finding the area to the left of this, or the probability of being 1.23 or less. And so I always start by drawing which part I'm looking at. And so I want the probability that z equals 1.23. So I'm going to go over to Excel. Make sure I can switch things here. So we'll come into Excel. And so I have Excel here. What I'm going to do is I'm going to set up some things here. I'm going to say that my z is equal to 1.23. So that's the variable we're going to use. And we'll talk about the probability, or the area under the curve, as equaling the probability of some particular z-score. Now, the command within Excel to do this is norm.dist. So the normal distribution. And notice it's going to ask for the x value, which in our case is going to be z for right now. So I'm going to put in B1. Now my mean for a normal, standard normal, the mean is 0 and the standard deviation is 1. And for all of these, it is cumulative, so we'll put true. So I use normal distribution, the z value, which in this case I'm referencing the cell back here. The mean is 0, and the standard distribution is 1, and it is cumulative. And so I get my probability, 0.89065. And so I have the probability. Now if I go back to our PowerPoint, 0.8907, there was a rounding on it. So that's how our technology can help us get what a particular z value is out of it. Now if we continue looking at this, we can look at the probability to the right, or for being larger than a z-score of 1.23. And we can use the idea of a complement. Since the area under the curve has to be 1, and we know the value up to 1.23, then we'll subtract 1 from it. Now again, in my process here, if I'm looking for the probability, I guess this should be the probability that z, let me get on the right screen here. If z is less than 1.23. If I want the probability that z is greater, the probability of the z-score being greater than 1.23, then I'm talking about this area to the right, greater than. So I'll do the probability that z is greater than 1.23. Well, our calculation is then to use the complement, because this is going to be 1 minus the probability that z is less than 1.23. It's the other side of this. And in Excel, to find the complement, so we'll say that z is less than, so for z to be less than 1.23, we have this. For z to be greater than 1.23, then we'll look at the probability of z greater than 1.23. And what I'm doing here is I'm cleaning up my notation. Well, then, and this is the complement. And so the complement is 1 minus the normal distribution. My x value in this case is going to be B3. My mean is 0 for a normal curve. The standard deviation is 1. And being cumulative is true. And this gives me the complement. So we can use our technology to calculate these things. In fact, we're going to find that Excel really helps us calculate a lot of different things a little more easier than some of the other things we have to do with the function. Now, but if we need to find between two areas, so if we need to find the probability or the area between z negative 0.75 and z 1.23, let's draw out our distribution here, 1.75, sorry. So I'll come over here, I'll do this in yellow to differentiate it from the other guys. Let me scroll down a little bit. So if I have a normal curve, and I'm looking between z equals negative 0.75. Negative is on this side of the mean. And z equals positive 1.23. Positive is on this side of the mean. And so what we do is we take all of the area up to 1.23 and we subtract out all of the area up to negative 0.75. And that'll leave us the area in the middle. So if we get the area all the way up to 1.23, we have more than we need by all the area up to negative 0.75. And so we can look at this as the probability of z being greater than 0.75 but less than 1.23. The probability of z, or the area under the curve, between negative 0.75 and a z-score and 1.23, well, it's the probability of z being less than 1.23 minus the probability of z being less than negative 0.75. So we can subtract the two probabilities. And what this is going to look like in Excel is if I look for the probability, let me just turn this into, let me put z in the middle. So z, we'll wedge it in here. Negative 0.75 is the lower bound, and 1.23 is the upper bound. So the probability that z is in between the two this a little bit wider, and let me fix this. This should be a number, 1.23. Well, we know it's equal to the difference between the higher probability and the lower probability. So we're going to use the normal.dist, and our x value for the higher number, the 1.23, I put in cell C5. It has a mean of 0 because it's a standard normal and a standard deviation of 1. And cumulative is true. And I'm going to subtract from it the probability, or the area under the curve, of the lower value. And so I put that in A5. All right, see how it highlights A5, the negative 0.1 or the negative 0.75. It still has a mean of 0 and a standard deviation of 1, and the cumulative is true. And so Excel will calculate the area in between these two z-scores for us here. And let me get back to the chart here. Now, there might be some rounding differences because but the table's rounded and Excel is keeping a lot more precision, so just be aware of that. And notice here, this is showing how we can find this in Excel. It has a normal.standard distribution we can use by using the .s function. I'm going to avoid using the .s function, and I'm going to put in my mean and my standard deviation, and you're going to see why in the next section. But again, if we want the area to the left, we'll draw our curve and know that all of our distributions go from left to right. And so if we draw that point in, we know which value to put into our calculation. And so if we want to the right, then we use 1 minus the normal distribution. Again, in my examples, I'm going to use normal.dist, and I'm going to specify that the mean is 0 and the standard deviation is 1. And in the next section, we will look at why this helps us.